have used more power tools, but
yeah. We will be covering more as we go along. It's just a little bit tricky when you don't have, I don't know, because of lack of time. I'm trying to do this where the sequencing of things is a little bit smoother in terms of what to cover and which direction.
yeah.
So, yeah.
I actually have to say we went deeper into permutation groups than I remember from the last time I took group theory.
Okay, that's an interesting thing to hear. What about the rest? Are you all tired of symmetric groups? In fact, one thing I didn't mention here, maybe I will mention it in the next session. One of the thing, every finite group is actually a copy of a symmetric group. So they are very, very powerful. So it means that you can essentially just use SN if you have to play around with SN essentially.
Mm-hmm. On the other hand,
yeah, go ahead.
Well, this is something we'll be getting to. On the other hand, the bigger N goes, the more structure is in SN.
Yeah, and I hope also in the last session, I think in the last slide, we cover the alternating group, which is a very important group. This is the reason why there isn't a solution, a general solution for polynomials via radicals for polynomials of degree greater than or equals than greater or equals than 5. So it's really, really, really very interesting. Yeah.
Yes, that was a kind of a strong hint. Oh yeah, I noticed. I figured it out, but your last notation where you defined the alternating group as the kernel of a homomorphism, you actually just gave a mapping to the set plus minus. You didn't specify a group. It kind of doesn't matter because there is only one group with 2 elements, but it's a little sloppy.
Yeah. I'm glad you could very often sometimes one thinks it's like the structure is obvious there, but the audience, if the audience is not coming from mathematics, it's not especially if you haven't watched the lecture, because I think I commented what structure at some point or something in the session.
Yeah, and if you don't use the group structure, if you like naively think, oh, I can just add +1 and -1, it's not even a closed binary operation.
Yeah. And I think in the session I mentioned it's a multiplicative group that but maybe on the slides I should, because there's no guarantee that maybe some people will just skim through. They won't watch the full lecture and they miss that detail, and then they think, oh, how is this a group?
Yeah, and I think it's important that the homomorphism is between one group and another, not between a group and a set.
Yeah.
But I guess when we get to actions, that the notation there will make it clearer, the difference.
Yeah. Okay. I think we can just get started. As I was telling George, everyone on the thing. By the way, if anyone wants to join the stage, please feel free to do, because I think it's becoming a very narrow group now in this group theory crash course. Because I think a lot of people were aware of it too late, and they are not keen into, getting watching lectures by themselves and going through all the hassle. Yeah. In fact, I have someone commenting earlier in the week asking whether we will have another crash course on group theory. We will. Actually, there will be another opportunity to have a bit of group theory because I'm planning something on discrete logarithm-based cryptography with the emphasis on elliptic curve cryptography. So we will definitely review group theory again, and then with the focus again on cyclic groups. This will be a piece of cake for you guys because you've already gone through that. So, but nevertheless, it will be good to refresh. And it will be very interesting because with elliptic curves, you will be playing with an interesting group associated with them. So we will also obviously work with finite fields, and then define what an elliptic curve is. As a matter of fact, maybe we'll even go abstract to define at some point a abelian variety, which is a little bit more abstract. Elliptic curves are just special case. As a matter of fact, of hyperelliptic curves as well. Anyway, yeah, so there will be a chance to review again some basics of group theory, but this crash course will have more general stuff really, because in the one that we have planned will be mostly focused on finite groups. In here, we will at some point make a transition to matrix groups. So these will be more relevant. These are non-abelian groups, so these will be more relevant to quantum for those of you interested in quantum computation and these things. So yeah. Okay, so let's see. So I think we'll probably settle for 20 sessions. Let's see. If I'll leave it as an option. If there is a flexibility to add extra 2 sessions for those who want. If there is any need to go a little bit deeper on something, or expand our scope. I was tempted to maybe we should have 2 sessions on representation theory, a little bit about representation theory, and then that's it. You will dive more into it in the context of Lie groups, but maybe that could be an interesting thing to reserve 2 extra sessions just for representation theory. What do you think, George?
It's hard to say. It's good. Might be good to get a taste of it ahead of the Lie group.
Yeah.
And the trouble is that even in finite and discrete groups, it's a rich, active area. So
yeah,
you have to choose what additional topics you're going to cover once we've got the basics.
Yeah. Okay. So let's keep it in mind, everyone. I know that's one of the things that I know. There is this is actually a good thing to bring in the next slide, not this one. So, but I'll just mention this one briefly. So we are here. We're still in groups. We are in the borders. We are inside symmetric groups bubble. We are trying to get out. I'm trying to the most natural way of getting back to abstraction again. So, but we'll still in the next session we'll make the transition again. But some of the stuff will become a little bit more natural. We'll use actually symmetric groups as test use cases for some of the notions. You will see they will become so like concrete examples when we talk about actions, cosets, all this stuff. So the end goal is really to have to go to matrix groups. This is the thing. So you are refreshed because these are prototypes of Lie groups, and you won't understand why they are Lie groups. So behind scenes, you will just understand some baseline things about them. Be familiar with with their algebraic structure. Yeah, the topology geometry stuff will come in anything with the in the Lie group section. Now we are about next Monday, this coming Monday, there will be the first lecture of measure theory and functional analysis released. So I'm quite convinced that most of you now at the moment will probably be taking it, or at least have shown interest of auditing it. Is that the case for you, George, or anyone else on the audience?
Yeah.
Yeah, so it will start on Monday. So I already have the video for the first lecture. All the uploaded to YouTube is just to make it visible. Actually he had a great idea that I think it was worthwhile to try, which is to release the problem sets for the first 2 lectures ahead, so people can have some sense of idea about how the approach to problems and these things, and also the hand holding. I think the homework also, already hinting that this course is a great opportunity really to have someone like, more of a hand-holding thing than with what we have been doing. So you will have a little bit more extra support, which means like, it's a great opportunity really to push yourself, because he will provide solutions. He's giving hints, all this stuff. It's really great. I would say like life is easy. It's easier than what you've encountered so far. Yeah. So yeah. So I hope some of you will really go and take this thing. And yeah, maybe go and try to. I don't know, George. Have you seen the problem set he published on GitHub?
I looked at the first one, and the first problem, I could do even without calculus.
Okay, that's cool.
Just some classical math and analytic geometry, you should be able to do that.
Okay.
Without the definition of the Riemann integral. The second one, I had to say, oh my God, what actually is the definition of the Riemann integral, and review it.
Yeah.
So it's like a long time since I took calculus. This might be a hint to everybody to brush up on your calculus and or analysis ahead of this.
Yeah. James will obviously have a quick review of things, for that matter. He will definitely, try his best to, to meet people where they are, anything. But it will be like a quick review of. I think he shared. He published post a couple of weeks ago, 2 weeks ago, with the resources, recommending people resources, what to review and these things. I think if you do that, you will be fine in the beginning. The rest is like, measure theory stuff. You'll pick it up. For those of you who have like taken the topology stuff, the point set topology section of the crash course we did before, some of the actions will really resemble the actions that we went through with, except some subtle differences there. But in terms of abstraction, you will be, there won't be much of a shock to you in the system.
Dimitri says he's struggling with problem 2. Oh, problem set 2. Well,
okay.
You're jumping ahead. I haven't even looked at it until I finished problem set 1.
Okay. I think if I recall properly, I think that problem set will definitely require you to have already the basics of the sigma algebra stuff that he will be touching. But yeah, that's a good thing. Okay. And another thing I want to share, this is more like the thing that we finally decided to create a LinkedIn page just for quantum formalism, and then maybe we will just start posting interesting stuff, maybe interviews or whatever, if hopefully at some point, people will feel comfortable to write blog posts, about their experience with the community, or even opinions and these things about learning abstract mathematics, these type of things. So we will be happy to host you to write. Just feel free to reach out, write something, we'll post it for you. Be a guest writer. Share your experience. Share your thing, your views. Okay. And now to the thing, we are covering so little. I'm like a bit anxious and afraid of even making typos, because this is so little we are covering, even though I was in a rush. So let's see how it goes. So we will come to a notion of orbits in a more abstract sense, but let's start with this one using the symmetric groups, the permutations. So giving a permutation, an arbitrary permutation, it doesn't have to be a cycle, okay? And an element I from this set 1 to n, which is where this symmetric group is the set of symmetry of it, right? the orbit of this element I under the thing. So the orbit is always, in this case, is under, the orbit is under the permutation, is defined as this set. So you take the power of the permutation to an integer, and then apply the result of it to the I. Okay, so this is also obviously this is a finite set. You can see this, right? And I'm being very nice to Rick. I hope I didn't make any typos this time, because the last time there was quite a few annoying typos in terms of the group exponentiation. Remember, I'm using R here instead of K because we will talk about K cycles to not confuse people. So refresh lecture 6, given a group G, let's say the binary operation star, well, in this case, the symmetric group, we call this is the composition. So the star would be the composition of maps, okay? And the identity E, in this case, concrete example, in the symmetric group, the identity will be the identity map, right? So giving an element of G and an integer, the exponentiation is defined like this: G to the R equals the identity if R equals 0. And then is equals this, G time star times, apply with the star operation applied to it, R times if R is positive, and then the inverse of G, because G is an element of a group, then it does have an inverse. So the inverse of it, you apply the binary operation again, R times to it if R is greater than, less than, is negative, is less than 0. Okay. So another thing also is, you will recall this basic property of this exponentiation. So if you have an element in the G, for any element in the G and 2 integers, you will have this. And most importantly, very interestingly, you will have this. And this is actually the last property 2. You remember, this is behind the Diffie-Hellman key exchange protocol, right? This is the basis of it, So this is I hope you understand this. I didn't want you to go back to another slide, so I decided to add this. And let me know if there's any typo. I don't see any typo. George, can you see any typo?
It looks good.
Yeah. Okay. So that's the thing. So this is a finite set, and it's a subset of this. So this is important to know. It's not a subset of the permutation group. Okay. So orbit is a subset of the set. Okay. Later you will see, when we define the other more abstract notion of orbit, there's something also called stabilizer, and these things, you'll see the difference of it. And you will see the other orbit. The orbit is. I want to jump the gun. Yeah. Okay. So now we have this proposition. I hope I phrased it properly. If not, I will leave it as in the study group to see if we can make a cleaner proposition. So proposition 1.0, let sigma be a permutation, again an arbitrary permutation, and then I be an element of the set, of the underpinning set. Then this proposition is saying that there exists an integer, a positive integer, such that this thing is verified. Now, the proof of this is actually not very hard. It's a little bit more, a little bit, I won't say too technical in a thing. It's a bit, it requires a bit of hard work in some sense. Not that hard, more like time stuff, but maybe you could try to prove this for like, for like simple toy examples, say, for example, S3, for instance, and see. And then the next proposition, I hope I didn't make any typos. is that this follows the construction from this. If sigma is an arbitrary permutation again, and let's suppose that R is the smallest integer. Okay, so this exists. This is actually there's a thing as a consequence of that. There must exist a small, the smallest integer that satisfies that, such that this is satisfied. Sigma to the R of I leaves I unchanged equals I. Then this is telling you that the orbit then can be computed like this. Does this resonate anything to you? When we were in the cyclic groups things, yeah. And its cardinality is R minus 1. So this means that essentially what we are saying is that the orbit of I has distinct elements. Okay. And this actually can help us. This is a way of computing orb of I. So the hack is you try to list. You start by listing, in sequence. You put I, and then you go sigma of I, and then sigma 2 of I, and then the moment you hit back to the thing, that's where you stop. And then then you have the entire orbit for you in there. And then another thing is this one here. This is there's a challenge here. So suppose you have again a permutation sigma, but now you have I and J be in this in this set. I added it to be X because I needed the abbreviation here. So it's the same set that we've been working on. It's just a laziness. We can define a relation, this, should I call it tilde sigma or something? How would you call this, George?
Too many squiggles. I would have to think.
Yeah, it's one of those things you can read it, but actually you can mathematically, formally look at it and know it. But the nomenclature, yeah. This is so anyway, this object here.
If we even go to a functional notation, call it sigma paren I mean, tilde paren of est. It's important that it's about sigma.
Yeah. Okay. So we can define a relation on the set X via this. So we say I is equivalent to under the sigma, right? Is equivalent to J if there exists an integer R such that this thing is satisfied. In other words, if J is in the orbit of I. Okay. Now the claim is this is defines whether this defines an equivalence relation. What do you guys think? For example, it's easy to see that obviously I is equivalent to itself because I belongs to its own orbit, right? Tilde sub sigma, yeah. Yes, thank you, Barry. Yeah. So the question then is, do you all agree this tilde sub sigma defines an equivalence relation on X?
That's the infamous, it is easy to see.
Well, this is a thing to put pressure on people to say it's easy to see, and then you'll say, you know what, I spend all my time. How is this easy to see? This is actually a motivation. I used to have a professor who used to do this. He'll say it's very easy to prove this. And actually, there are some stories actually on some schools. I think it's Oxford or Cambridge. One of them, they give open problems to grad students without telling them. Sometimes they reward them. They change the way the problem is stated, but it's equivalent to actually solving the unsolved problem. And sometimes they succeed. Some bright guys end up making progress. And they said, "Oh, it's easy. It's easy for you. It's a piece of cake." Yeah. But in our case, this is Go ahead, George.
I think it's easy in the sense that there's nothing deep, but a little tricky in dotting the I's and crossing the T's and checking all the definitions.
Yeah, that's true. Yeah, that's true. And I guess if you've already gone through this, you might agree it's easy to say it's easy. Yeah. But yeah, this is indeed, you can verify this is, I can tell you, this is actually defines an equivalence relation on X. Yeah. So you have to if you don't see this, you need to just go back to the definitions and work through things again. But I think most of you now will be able to see this is indeed it's an equivalent relation. And the reason why you needed this, because this theorem here, we already seen in the previous session that any permutation can be decomposed as a product of two cycles of transpositions. And here's a general thing to say that given any permutation, sigma can be written as a product of disjoint cycles. Okay. This again, there's a bit of technical thing to go around to prove it. It's not that hard. It's just about putting pieces together. But one of the ways to do it is to, first of all, you find all the orbits under sigma, right? And then for each orbit, you should be able, you get a cycle. And then with those cycles associated with those orbits, the product of them should yield the sigma. So this is a way actually you can verify this with a toy example. For example, you could try this with the S3 to see. So you don't need to prove this in generality. Just go with the toy example just to give you an idea. So that's it, really. It's very embarrassing. I didn't have time to. I wanted to start with the group actions, today, but I think we just close here, and maybe for those of you who are struggling with the other stuff that we with this cycle stuff and other stuff, just it's an opportunity to just review, have an easy session today, and then in the next session we'll pick up with the group actions, and things will start to pick up. This will go into other stuff like cossets, all these other things, and a few other important theorems you'll learn.
Okay, yeah, the pieces are coming together. I think I see that techniques similar to solving the previous challenges will help with this.
Yeah. This is why it's like everything is like this is like a continuation really of some of the stuff that you learned before. So they're like I mean you've been through before. So it's a good way to transition to a new to end. I mean, to start to exit. We haven't exited yet symmetric groups completely. And you will see some of the stuff will come back, come to play again. In fact, we'll use them as toy examples when we talk about cossets and all this stuff. We'll use SN, for instance. So familiarize yourself. Any questions? I know I'm really sorry because we haven't. Maybe try to prove as a challenge. Try to prove the general cases for some of the propositions, for instance. Try hunt for errors or something that maybe there's something there. Yeah.
Or for small n, say less than 5, try and find all of the subgroups.
Yeah. That could be. Yeah. Yeah, it's pity I didn't have enough time to do the we would have started with orbit. But I think you have enough here to go and play around with, at least even on the computational thing, to try to compute. Go and play with orbits. And then we will come back to an abstract notion of orbit when we in the next section or the session after or so. And then your challenge then will be to see how does that connect to this. Is this a special case of that? Orbits are very all these stabilizers and these things will show up in things, especially when dealing with specific type of groups for like have like important applications. Yeah, I think Bob here actually. Bob needed orbits and stabilizers, I believe. Is Bob here?
He's on the list of little people icons, but
okay. Oh, he's not active. Yeah, I don't think he's active at the moment. Yeah, because after we go through orbit and stabilizers, I think Bob will do a guest talk about the application of these into some, what was it? Which area is it? Geophysics or something?
I think it was crystallography.
Okay, crystallography. Yeah. So it's an opportunity to see these things applied in this contest. Yeah. Okay. So any other comment? I guess we can just comment about upcoming stuff. Maybe the measure theory stuff. At let's say midnight on Monday, UK time, midnight, the thing will be alive. So you will, those of you who are awake in the US, you will be able to have a preview of the lecture, have a few hours ahead. So that will be probably, I don't know how many hours difference between you, probably in some places, maybe 6 p.m. your time or something, or 7. On Sunday, yeah.
Or if we have any Asians or Australians on board.
Oh, yeah. So it will be Sunday for you, Monday for the thing, for the Europeans. I really look forward to it, because this is a new format, and I already if it works out like as we think it will, we will adopt this format. It might not be to do with maybe we can adopt live lectures together with this problem set stuff with tutorials and these things, because in the other course that I'm planning with the other guys on elliptic curve stuff, they might not have time to be like recording and using all the stuff that James does because they haven't done it before. So it could be that they will resort to more or less like my format, but with more like more tutorial added to it, hands-on like a tutorial. Yeah. So we'll see if some of them are interested in recording and use the same thing as James. That's fine. Yeah. And George, what do you think about the format of the problem set? So for each lecture, after the lecture, we really obviously we release the first 2 sets, so that doesn't it's already broken the convention. But the idea is the solutions will be for the previous lecture will be released in the next lecture once the next lecture is released.
It reminds me more of the traditional college experience, where you would, after a week or however much time, have a review session with the teaching assistant, and at that point, if you hadn't solved them, you would see the solutions.
Yeah. Yeah.
But it might, for some people, be a motivation problem that if they get stuck, to just wait rather than pushing ahead. We'll have to see.
Yeah, that's the thing, you know. I hope that will not be the case. If anyway, I mean, I hope it would be actually more motivating to say, you know what, I have nothing, I will give it all. You know, if I get it wrong, I know at least there is it's in the thing. But you are right. Some people might just wait for the solution, but then, you know, they're not. It's not like you know, it's not the ideal. You know, they're not learning. You know.
But on the plus side, you know, if there's a solution to be given, you're not going to be given a trick question that turns out to be a research problem.
Yeah. That's true. Yeah. So we could sneak some open problems there and then say we haven't had time. James hasn't had time to solve it, so we'll push it again.
I have an elegant solution, but there is not enough room in the margin.
Oh yeah, who said that? Fermat, wasn't it? Yeah, that was the classic one. And then it took you know, sophisticated mathematics that there's no way that he would know how to solve like abelian variety and these things to solve it. It's like it would be like very interesting that if indeed he had the solution, what did he use to actually how did he find the solution for it? You know, how did he find the proof? You know, because surely they were not you know, all these abelian variety stuff, all these notions were not were not born yet.
And you know, and there, even though that's a very complicated, difficult proof, there is no proof that there isn't a simpler proof.
That's true. That's true. This is what makes it very very interesting indeed. Yeah, that's true. There could be an elegant proof, very simple, that he found, but then, you know, yeah, that's true. This brings us also to cryptography, you know, that we'll say all these algorithms, you know, the existing algorithm cannot, but it doesn't mean someone else cannot, hasn't found
Yeah.
something like, you know, a shortcut or something to do it. So, yeah, it's fascinating. Is there anything else? Maybe we should. I know we have just not much today to cover in terms of content, but at least maybe some of the challenges are interesting to go and refresh, and also to give you a little bit more easy thing to, because the functional analysis stuff, for those of you taking it, is starting this Monday. So yeah. Yeah, someone posted a link.
Oh yes, I had heard about that.
Oh yeah. This I think I sent a newsletter also about this somewhere. Yeah, it's true. Yeah, this is actually very interesting because they use techniques in algebraic geometry. You know, that you could argue that maybe the reason why these cryptographic protocol, these that were proposed, you know, people haven't found loophole yet, is because, you know, people haven't been exploiting these advanced mathematical machinery in order to try to break them. That's the thing, because the stuff that actually I one of the guys that we are currently collaborating with is coming from arithmetic algebraic geometry. It's the thing he is actually looking at it. You know, there's no way that someone like you know, who some of the techniques that these guys use, some of the like results in the field, not accessible to everybody, you know, even like you know, especially cryptographers in the technical industry and these things, you know. So yeah, so it's well possible. This is one of the, it also makes the case for, you know, having it's also like makes the case that it makes the case that maybe the more mathematical, sophisticated mathematical machinery that's available out there, it will help people, not just build better cryptographic systems, but also try to break the existing ones, using existing techniques, using these new mathematical machineries. I mean, yeah. For example, there are some rumors flying around this being for some time, in this thing of Bitcoin, for example, it uses for their digital signature, it uses elliptic curve. Why did Satoshi Nakamoto chose that particular elliptic curve, for instance? Is there a backdoor actually or anything? Nobody knows.
Behrend has a very interesting question. Can you prove that a cipher cannot be broken?
Well, that's a very, very interesting question, and I do. And I don't think you will find anybody will tell you there is give you the answer whether there's a general proof that you can break a cipher or not. But algorithms, yeah, if you have a specific algorithm, you have a specific cipher, what then you can say, okay, this algorithm will not be able, for example, to break this on the thing on a reasonable time, for instance. These type of things you can do that, but to say that it cannot be broken, this is a very interesting question.
Yeah, like just even the RSA, based on the difficulty of factoring a large number, that is only based on the algorithms that we have.
We know
take so long. There is actually no proof that a better algorithm doesn't exist.
Yeah. So it's a very interesting question.
But there might be. I'd have to think about it from a complexity point of view, that there might be a problem that you can prove is intrinsically complex.
Yeah, I mean, you can always do that from a complexity point of view to say, how in terms of complexity, this thing is hard, and in a sense, it makes it like, our existing techniques are, the thing from our existing known stuff, knowledge and all that, it's intractable. But as I say, this is going back to the popular thing, never say never.
Yeah.
Or never say everything is like, there is nothing like, you hear a lot of these cybersecurity companies, selling things to say, it's our thing is secure, it's unbreakable, and these things. Say what? You are lucky that maybe there's someone behind scenes, already broken your system. They haven't announced it, or you are inviting someone to come and.
I think the problem is that you want your key that gets exchanged to be shorter than the entire message. If you have a provably random or provably pseudo-random key that is as long as the message, then that can only be cracked in the order of the exponentially in the length of the message. But if your key is shorter, which in practice you almost always want, that's a little trickier to prove.
Yeah. Speaking of key stuff, this is one of the things that the efficiency of using elliptic curves, for instance, because they are more they enable you to get the same level of RSA to use shorter keys. You should probably come into the course on discrete logarithm based cryptography, which is essentially based on the discrete logarithm problem that we covered a couple of weeks ago on in group for groups. In this case, there are specific type of groups that this thing is hard to solve, And this is the thing with cryptography is always, you want the problem to be hard to solve, but also from an implementation point of view, you want something that's fast. You want an algorithm, you want something that's not too slow, something that's effective in terms of implementation, as much as hard mathematical theoretically to break. That's the thing. Yeah.
And in practice, you kind of want to distinguish between data in motion and data at rest. Like if you can say that it's good enough to show that it will take more than an hour to break this code, that's good enough if it's just a one-time login or something that will change.
Yeah.
On the other hand, if you've got your secret plans stored in a file somewhere, you want to be sure that given all the computers in the world and 10 years that it can't be cracked, and that's a much harder proposition.
Yeah, this whole thing also, this is a bit related. This is also a bit detracting, but I guess it's worth mentioning, this thing of all this thing of harvest now, decrypt later, fear mongering that's going on at the moment. Quantum thing. Yeah, people like, you need to get ready now. But actually, very interesting. A lot of companies, I think, they are prematurely selling post-quantum cryptographic solutions because obviously they are, venture-backed. They need to show. It will be funny, some of the algorithms that they are using, even the ones that NIST has proposed, someone in the next few months come up with, with a genuine mathematical attack, and then, the whole thing comes crumbling.
The one thing that we have learned is that you can't get away with using a quote unquote secret black box algorithm.
Yeah, it doesn't. Unfortunately, there's still some companies that are saying that thing to, it's a bad idea, because, you can't just rely on this to think that your algorithm is like the stuff is uncracked, by hiding some sort of secret, that's the strength of it, and it's just you want it to be attacked, the security of it is actually on making it, there's something called the Kirchhoff's principle, right? That says everything in the thing everything should be like public, essentially. Yeah, except one piece of information, for example, your keys and these things.
Yeah.
Everything else, how you construct the algorithm, how do you think, if your security relies on something else, on the actual method of then it's really like it's a bit dubious, because who to tell that one of the gruntled employees of the company will leave, take the secret with them, right? Then it's no longer, there's nothing you can do about it, right? So.
And and anybody that claims they have the secret black box, how do you know that they haven't put a back door into it?
Yeah. How do you analyze? How do you kind of So it doesn't. Yeah. Obviously, in the past, I think there were some controversies with the NSA and this thing getting involved with NIST in some of the standards, trying to sneak in But again, this shows the thing, because people, then it became public. It became people became aware of all this stuff. It eventually came out, So yeah. There is one guy who was actually, I think, I saw somewhere, I didn't read it properly. He was going to sue NIST or something for their thing in relation to the post-quantum cryptographic thing. He wanted to know what I think along the line. I'm not sure the details, but how come they select? How was the selection process and this thing, and how much influential the intelligence agencies were, and all this stuff. I think something like that.
Yeah. But I guess the moral for us is that the more abstract math you understand, the better prepared you are.
Yeah, absolutely. And I think this is exactly this this example of this post-quantum cryptographic thing being cracked using a very advanced technique in algebraic geometry. This was like published like I think less than 20 years ago. This thing. So in the realms of mathematics, this is new. Yeah. So it shows there is a lot that mathematics can help, especially these advanced branches of that class as pure maths, finding their way into things. This is actually very fascinating to me, indeed, and I think there is still a huge potential for exploitation in these things. That's one of the reasons we want to do this, step by step. Because the more we end up all benefiting, the more people have access to mathematical machinery. I think the more they can do stuff in the emerging industry. The same with the AI. People talking about AGI. I think just by following the approach that people are following nowadays with these heuristics and these things will not get there. We'll need some a general theory, something more foundational and these things, and that comes with mathematics, the language of mathematics. This is what will lead us to better architectures. To see that all these architectures that people are coming are actually special use cases of a much more broader thing. Yeah. So equip with yourself with mathematics. That's the thing. And obviously, it's a massive field, right? And George, that people say Poincaré was the last universalist, like.
Yeah.
The last one to be able to have their feet. He's involved with this back in his time anyway. The mathematics, all the mathematics that was available nowadays, everything is more specialized in these things.
Although on the flip side now, they discover connections between separate things that went off specialize, and then later on a deep connection emerges.
Yeah, it's true. And there's a whole program like is it Langland's program, to try to unify, different branches of mathematics that definitely had a lot of impact in the thing, And I think Andrew Wiles' proof of the Fermat last year, which looked like a number theory problem, but then it needed so many other tools, that intertwine tools across branches of mathematics in order to solve it. Okay. I think only us left. Yeah, Dimitri, us, and Barry. So maybe we can.
All quiet on the chat.
Yeah, I wanted someone to. Nobody wants to come on stage and make a point. Did I put open stage? Maybe I didn't. Let's see. Anyone wants? We can use this. It won't be broadcast. I will cut this thing because it will be too long. So we could make it like. Yeah, the stage is open, so anybody wants to join, ask any question directly or make any point, feel free. Yeah, I won't. If you don't want, I'll cut this from when we ended just to make it short for those watching on YouTube. So, in fact, I can stop recording now. That will make people more comfortable. I know we are also running over the hour anyway, so yeah.
Okay, so